Any questions before I get started? If not, I will continue talking about what's known as U-Substitution. Now, I'm going to show you substitution, a host of examples before I cover the theory. The theory is not especially exciting, but I mean, the proof is really in the method. If it works, it works, you know. So here's one. And we're on page 230 if you're keeping score. So here's x e to the x squared dx. All right, so here we look at it and go, well, I'm going to let u equal to x squared. All right? And if I do that, then du is 2x dx, yeah? So I usually multiply the dx to the other side, all right? So, I mean, du dx would be 2x, right? So that means if I multiply the dx to the other side, I get 2x dx. Now, you'd be like, what do you mean multiply the dx to the other side? That's just formal nonsense. Well, fair enough, it is formal nonsense for us, but it is formal nonsense which, this idea that you can multiply the dx to the other side, it's a useful mnemonic for remembering the method, if nothing else. So I'll leave it at that. Now, okay, so look, I can solve for dx, right? Dx is du over 2x, is it not? So with that in mind, I make the substitution. I've got x e to the u times du over 2x. So this is one way you can do the u substitution. You can make the you state what u is, solve for dx, plug it in. If you made the right substitution, things will cancel out. See how things cancel? This gives us 1/2 integral of e to the u du, right? Well, that's great because, of course, that's a elementary integral, right? So that's 1/2 e to the u plus a constant, and then I go back to my substitution. I have e to the x squared plus a constant, and there you have it. And of course, if you doubt me, you can differentiate the answer and see that you get back to the integrand, right? The derivative of 1/2 e to the x squared is, in fact, x e to the x squared by the chain rule. Example 2. We have integral of ax plus b to the 13th power dx. And we're given that a is not equal to 0. Right? So in this one, what do you think I should let u equal to here? How about ax plus b, right? I mean, do you guys want to like expand out ax plus b to the 13th power? We'd be here a while, right? You could do it. Just take that Pascal's triangle, get out to like the 13th row. Go nuts. No, let's not do that. Let's let u equal ax plus b. So du is a dx, or if you like, dx is du divided by a. So there's my substitution, and it's going to give me, this is the integral of u to the power 13 du over a, right? Which integrates to give me 1 over 14a u to the 14th power plus a constant. So put it back in terms of x. I've got 1 over 14a ax plus b to the 14th power plus a constant. There's your answer. Now, do you need U-substitution to do this problem? I would argue no. I think that there exists a pretty wide percentage of students taking this course that could guess this as an antiderivative. I don't think this is outside the realm of guessing, this example. Right? Would you agree? I mean, if you really stopped and thought about it, what function can I differentiate to get back ax plus b to the 13th? Right? You might try this as the antiderivative, what we just wrote down, right? But U-substitution gives us a clear path to derive it. Example 3. Integral of 5 to the x over 3 dx. So I'm going to let u equal to x over 3. So du is 1/3 dx. Or in other words, dx is 3 du. Make my substitution. I have the integral of 5 to the power u times 3 du. This gives me 3, pull the 3 out, right? Integral of 5 to the u is 1 over log 5, 5 to the u plus a constant, so finish it 3 over log 5, 5 to the x over 3 plus a constant. Again, I will ask any questions.
Like just how you decide the u.
Ah, yes, the always asked question. How do you decide the u? Well, that's a good question. But there's no easy answer to it. I mean, the best answer I can give you is you practice. A slightly more structured answer I can give you is you have to think about what you're trying to do. What you're trying to do is to take the integral which you're given and change it into an integral that you already know. So that does inform your decisions some, right? A lot of times, whatever's the ugliest thing looking in your example, that might be what you want to make the u. Other advice includes try something. See how it goes. If it doesn't go well, try something else. What would it mean for something not to go well? Well, here, I'll give you an example of something not going well. Example 4. If I had integral of, x cubed e to the x squared. Well, let's see, I'm trying to think here. I have a really hard time coming up with non-examples. Give me a second. I need something that doesn't work. That's a harder problem. Here's one that's not going to work no matter what we do. But you might try integral of e to the x squared dx. Actually, the answer on how to integrate this only comes in Calculus 2. And there it's only in terms of something called a power series, which is sort of the infinite extension of the Taylor polynomials we did. But if you were to try to do this with U-substitution, you would do what? You would let u equal to x squared, right? You'd try that. Just like the first example I just erased. And then that would give you 2u, du is 2x dx, right? So dx would be du over 2x, right? And it's not going to go well for us here because we're going to have integral of e to the u times du over 2x. And so this is a dead giveaway that, like, no. To quote my community college professor, this dog will not hunt. This 2x, we cannot ignore it. That means fail, right? Fail. The substitution has failed because you don't have an expression just involving u. For the u substitution to work after we make the substitution, which involves two pieces, changing the integrand from x to u, but also changing the dx from something with dx to something with du, right? Both of those things have to be done for these indefinite integrals, and they both have to work out in concert in such a way that all of the x's cancel out. If that doesn't happen, you haven't made the right u substitution. And it may not even be that there is a right u substitution to make. It can be proved that this actually is not integrable in the sense that we're doing right now. In other words, you cannot write down an antiderivative for e to the x squared in terms of products and sums of elementary functions, like the ones that are in our lexicon of functions. You know, sines, cosines, coshs, sinches, exponentials, algebraic functions, and the rest. Now, the proof that that can't be done involves something called differential Galois theory, and like it's not something that I'm really that well versed in, but I know a little bit about these things. But to prove that you can't do it, man, that's a really hard problem. And yet, we know that an antiderivative exists in principle for this function because it's continuous on the reals. So yes, an antiderivative exists, it's the area function, but that doesn't mean you can find a nice formula for it. See, we're looking for nice formulas for antiderivatives. That is a more, that is a harder problem than just saying that there exists a function which differentiates to the other thing. Like you can have the existence of a function which you can't find the formula for. I know it's kind of hard to wrap your mind around that idea, but it's there. Here's one we can do. And you know, something we haven't done yet, but now we can. Integral of tangent. Now this one, sometimes you just need to like put all your cards on the table before you try to do it. Like this one will not go well for us unless we make another step. All right, so I'll make that step for us. This one, like you could try u equals x, you could try u equals tangent x, it wouldn't really go very far. Because you would, again, if you tried u equals tangent, you'd get the same kind of problem you had there. Because like the derivative would give you secant squared, which you don't have, and you wouldn't be able to cancel it out. So like if I tried u equals tangent, it wouldn't work. So try something else, which is just to write it out. Like this is sine x dx over cosine x, yeah? Because a tangent is sine over cosine. Now, there are sort of two things you could try here, right? You could try u equals cosine. You could try u equals sine. My general advice is make u the ugly thing. The ugly thing here is the thing in the denominator. So I make u equal cosine. And if I do that, then du is minus sine x dx, right? Now, I have solved for dx in all the problems so far, but you don't have to do that. You don't have to solve for dx. If something pops out at you, like this one does for me, which is that sine of x dx is equal, sine of x dx is equal to, well, it's equal to minus du. That's just readily apparent that I want that, right? Because that's right here. See that? So I can trade sine x dx for minus du. Cosine is u. There we go, done. So if you're wise in the way you substitute, you can even avoid a step, the canceling the x stuff step. In Asia, there's commonly taught a notation which even avoids expressing the u. There's a notation for this which you don't even have to write down u equals something. I'll show you that next. But before we do that, let's finish this one. This is minus the natural log of the absolute value of u plus a constant. Remember, we need absolute value. right? And that's what? Minus the natural log of the absolute value of cosine of x plus a constant. Now, that's not typically how you'll see this answer written. If you look at an integral table, you're likely to see this written as natural log of the absolute value of secant of x plus a constant. So notice that minus the natural log of absolute value of cosine is the natural log of 1 over the absolute value of cosine, right? Which is the natural log of the absolute value of 1 over cosine, which is the natural log of the absolute value of secant x. And so that's why we can go from here to here. But there you go. So hooray, now we can integrate tangent. Slick notation for U-substitution. Here's one. If we were integrating, let's say, I'll do 2, well, I won't do 2. I'll do sine of x squared, get it eventually here, x times the sine of x squared dx, right? Check this out. You could rewrite this as the integral of the sine of x squared times 1/2 times the differential of x squared. See, that's 1/2 the integral of sine of x squared dx squared. Which is minus 1/2 cosine of x squared plus a constant. There you go. That's U substitution without even writing the U. Very sneaky, yes? So this notation is, if we let U equal x squared, right? Then du is d of x squared, right? Which is 2x dx. So of course x dx is 1/2 du is 1/2 d of x squared. I don't suggest you use this notation. I'm just telling you, if you really, really like it and you're good at it, you're welcome to use it in my class. I don't use it because I think it loses students. Am I right? Yeah. So I will keep writing the u for you. Example 7. Well, let's do the integral of hyperbolic tangent. What do you think we should do here? Break it up again. Sinh and cosh it, yeah. So sinh x dx over cosh x, yeah. And how about a u? What would you like to make u equal to? U equals to cosh, very good. So du is sinh x dx. Oh man, this one's even nicer. This is just du over u, which gives us natural log the absolute value of u plus a constant, which of course gives us natural log the absolute value of cosh x plus a constant. And if you like, you can drop the absolute values, because the natural log of the hyperbolic cosine is the same. I mean, the absolute value of cosh x is equal to cosh x, right? How do I know that? Because cosh, remember, looks like this. Its smallest value is 1, and it opens up. Cosh x is greater than or equal to 1. So for what it's worth, I could write the answer like this. That's probably the best answer I can give here without getting further off track. We're not off track at the moment. Like, this is a totally legit example. And I think you should probably know it would also be easy to do cotangent and co-hyperbolic tangent, right? The coth, if you like. Let me look at an example of a different flavor, if you will. Integral of, let's see here, x cubed dx divided by 1 plus x to the 8th. So you can compare this example to example 9, which is similar but different. X to the 3rd dx, I'll put a 4 up here for my convenience, over 8, plus x to the 4th. So like this kind of problem, I would just make u equal to the denominator, and we'd be good to go, right? Like this one, you let u equal 8 plus x to the 4th. You got du is 4x cubed dx. So this gives you integral of du over u, which gives us log of the absolute value of u plus a constant, which is log of 8 plus x to the 4th plus a constant. I don't need the absolute values because the thing inside the log is positive, but anyway. But the one above is not like that, is it? I can't let u equal the denominator. What should I do? So xu, making x equal to u just takes you right back where you started, replacing x with u. So that won't, I mean, you can try that, but it doesn't go anywhere.
What's the difference even? Like, why can't you do that?
I mean, I can do it, sure. This doesn't help.
So set times to the right, travel there.
I mean, okay, but that's the same problem, just written with the letter u instead of the letter x. It's not, we haven't made progress on the problem by making that step, you know? Don't write that down. I mean, you can write it down if you want. I can't stop you. It's a free country. Sometimes. What were you saying? Here, I'll write a suggestive calculation. This is x cubed dx divided by 1 plus x to the 4th squared. What would happen if I make u equal x to the 4th here? So like x cubed dx is 1/4 du. And so what I got is 1/4, I'll bring the fourth out front, integral of du over 1 plus u squared. Do we know that integral? A useful exercise, so we've talked about integrals in terms of x. One useful exercise for you guys is just to go for yourself and write all of the elementary integrals using the letter u instead of x. It'll reinforce how the integration rules work, and it's just helpful also just because sometimes we don't see things except in their letter that we're working, you know, but like what I'm talking about, let me start making this list. Start out with a simple thing, you know. The integral of u to the n du, u to the n plus 1 over n plus 1 plus a constant, right? The integral of du over u, natural log absolute value of u plus a constant, right? The integral of e to the u, du, e to the u plus a constant. The integral of a to the power u, du, 1 over the natural log of a times a to the u plus a constant, right? The integral of cosine of u du minus the sine, plus the sine of u plus a constant. The integral of sine of u du minus the cosine of u plus a constant, right? But here's a couple other ones. The integral of du over the square root of 1 minus u squared. Well, that's inverse sine of u plus a constant, right? And the integral of du over 1 plus u squared, well, that's inverse tangent of u plus a constant. So part of the reason I asked you guys to derive the derivative of inverse tangent on test 2 is it's an important derivative to know in your heart, right? I don't look these things up, I just know them, you know. You should do the same. Otherwise, you're just like spinning your wheels if you have to look these things up. I mean, you do guys, I do allow you to have a card, right? Or is it a card or is it a page? I forgot. You're like, yeah, you're an honest bunch. It's good. Sometimes I get people trying to change the rules of the game when I ask a question like that. But yeah, I mean, so whatever you're kind of like a little iffy on, you can put it on your card, right? But if you have to look at the card actually, and I just think the more you know of these basic things, easier it is for you. So anyway, this, and it's also important here because it informs your algebra, right? Having the knowledge about inverse tangent being this integral, it prompted the algebra that I did because I knew where I was going. I knew if I could get it to 1 over 1 plus something squared, that's an integral I know. It's inverse tangent, right? So this is 1/4 inverse tangent of u plus a constant, right? And then you go back to where you started. 1/4 inverse tangent of x to the power 4 plus a constant. Does that make sense? I mean, it may not be familiar yet, right? That's why I'm showing you examples and hopefully learning together maybe. Let's see here. Another example, what if we're faced with the integral of the cube root of 1 minus 3x dx? I would say this one's a little bit easier than the one we just, well, I don't know if it's easier. It's about the same difficulty, honestly. What do you guys suggest we make u equal to here? me ask you the question. If we had the cube root of u, could we do that integral? I mean, we could do that integral, yeah? So let's let u equal 1 minus 3x. So then du is minus 3 dx. So dx is minus well, it's du over minus 3, right? So I got a, minus du over 3. I'm going to rewrite this just a bit. Minus 1/3, integral of u to the 1/3, right? I'm about to retire this chalk. 1/3 du. And we have to do what? We do minus 1/3 u to the 1/3 plus 1, which is 4/3, divided by 4/3, which is minus 1 over 4 u to the 4/3. Forgot to add my constant, my bad. So what do we get? We get minus 1/4 times 1 minus 3x to the power 4/3 plus a constant. Once you make the appropriate choice of u and you follow, the math, it's not that bad, right? Here's another one. The integral of, I'll do it down here. I got room for this one. Example 11. The integral of dx over x plus b. Okay, so we just let u equal x plus b. So du equals to dx. Right? And that gives us du over u, which gives us natural log absolute value of u plus a constant, which is the natural log of the absolute value of x plus b plus a constant. So that one's not too bad. This next one's kind of scary at first glance. X squared dx divided by the square root of x squared minus x to the power 4, like that. And we're given x is greater than 0. All right, so, well, if I make u the thing, and see, like if I try u the thing inside here, if I try u as the radicand of the radical in the denominator, that doesn't go anywhere because if the derivative of like x squared minus x to the 4th would be minus 4x cubed, right? And I don't have a minus 4x cubed in the numerator, right? So making u just the thing inside the radical, that's not going to work. And if I make u equals to, I don't know, so I think this one, the best move is to start by like trying to do some algebraic simplification if we can. I think we can here because notice that this is the square root of x squared times 1 minus x squared, right? So that is the integral of x squared dx over the square root of x squared times the square root of 1 minus x squared. What's the square root of x squared? Generally, it's the absolute value of x, right? But it equals x here because x is greater than 0. So this simplifies to the integral of x dx over the square root of 1 minus x squared with that algebra in mind. See, because I get x squared over x, which simplifies to x. right? Aha, now what? How about we let u equal to, what do you guys want to do? Now I think we can let u equal to the radicand, and things are going to go well for us, because the thing inside the radical is 1 minus x squared. When we differentiate, what do we get? Minus 2x dx, right? Which is kind of like what we got in the numerators. That should work. So I let u equal to 1 minus x squared. That gives me du is minus 2x dx, which gives me x dx is minus 1/2 du. So with that u substitution in mind, I have the integral of, I'll bring the minus a half out front, minus 1/2 integral of I'll leave the half in there. Sorry, sometimes I have trouble making decisions. Integral of minus du over 2 times the square root of u, right? What differentiates to 1 over 2 the square root? Well, the square root, right? So this is minus the square root of u plus a constant. So the answer is minus the square root of 1 minus x squared plus a constant. I think at this point it is time for me to stop and make a comment, which is that is not something we could have guessed. Right? We started by finding antiderivatives by guessing. Could you have guessed that this is the function that when differentiated gives you that? I definitely can't, right? But U substitution paired with algebra gives us a path through the wilderness sometimes. What example am I on? Example 12. Here we're facing the integral of the natural log of x dx over x. And we're going to assume that x is greater than 0. So what was my rule for u as a sort of just a general rule of thumb? Make u the ugly thing. What's the ugly thing here? Yeah, natural log's ugly. So let's let u equal that and see where that takes us. So du, I'll write du dx this time, 1 over x, right? In other words, dx over x, well, dx over x is what? Dx over x is du, right? So what are we looking at? We're looking at the integral of, u du. The integral of u du. Can you integrate that? What's the integral of u du? No natural log, just in terms of u, in terms of the variable u. All right, well, I'll do it. 1/2 u squared plus a constant, right? If I asked you what the integral of x dx was, you wouldn't have flinched. You'd have been like 1/2 x squared, right? That's why I'm saying it's a good idea to go write this down for yourself, just to try to get it, in your mind. Etc., you know? There's something about changing the letter from X to U that makes you guys like slip on what you already know. But we shouldn't use X, right? Because X is already their starting point, and we need to do things in the letter U in this transitory part of the calculation. Okay, but now what we got? We got 1/2 natural log of X quantity squared plus a constant, and there you go. Here, I'll do an easy one. But I'll change the letter. Integral of sine of 3 theta. Ooh, d theta. So for this one, we let u equal to 3 theta. Du is 3 d theta, right? So that means that d theta is 1/3 du. Make that substitution. We've got sine of u times du over 3, which gives us minus 1/3. What? What is the integral of sine of u? It is, right, cosine, right, minus cosine. So minus 1/3 cosine of u plus a constant. And then go back to the theta. Now, could you have guessed this? Yes, I think so. That's why I have given some of the, like a lot of the integrals in your current homework set, mission 8, they involve this kind of U-substitution, the kind that you can just kind of guess, right? I don't think I have difficult U-substitution in your mission 8. That'll be the next one. All right. I think I've really only done one difficult, honestly difficult U-substitution in here so far, and that would be example 11. All right. Wait a minute, I've got 2 example 11s. Oh no! You know, there's a simple way to simple way to fix this. I'll show you. So over here, when I was writing example 11, I wasn't actually done yet. Like, what I meant to say is 11 plus I. There you go. See, now it's complex. That was kind of a joke. But if a joke is there and no one laughs at it, is it still a joke? I don't know. Maybe. These are questions I can't answer. All right, so moving on here, let's work at something a little bit snazzier. This is kind of the same example as 12. So I guess this is example 14. Here we're asked the integral of inverse sine of z dz over the square root of 1 minus z squared. Example 15 is going to be the integral of t times the cosine of t squared plus pi dt. Example 16 is going to be the integral of sine cubed x dx. All right. I'm writing them up there so I can drop this piece of paper. All right, so first up here, I think the thing we should do is notice that u equals to inverse sine of z gives me du dz, if you like, is 1 over the square root of 1 minus z squared, right? Because the derivative of inverse sine is 1 over the square root of 1 minus the variable squared. So that's pretty good news for the problem we're working on, because then, you can see from this that du is dz over the square root of 1 minus z squared, right? So where's my green? I haven't used green today yet. I got this little nub of green left. So this is actually the integral of u du again. So we know how to do that. 1/2 u squared plus a constant. And, but u is inverse sine, right? So 1/2 arc sine, or as it's called sometimes, inverse sine, quantity squared, plus a constant. And there you go. So it looks scarier than it is, right? Example 15 is, I think, a little bit easier. We're just going to make the thing inside the cosine the u, right? If we do that, if we let u equal to, t squared plus pi, that makes du 2t dt. And so we have the integral. So notice that t dt is 1/2 du, right? So I've got a t dt here, right? So that gives me 1/2 cosine of u du. Which gives me 1/2 sine of u plus a constant, which gives me 1/2 sine of t squared plus pi plus a constant. So that one actually was harmless. It just looks kind of a little bit scary at the start, but it's not bad. Although I think I may be off the camera now. Woohoo. No, I got it. So what about sine cubed? How about this? How about we rewrite this as the integral of, because we've had really good success with the balancing between sine and cosine for the tangent example, right? So we hope that we can make something like that happen here again, all right? And so just notice that this is sine squared x times sine x dx, right? But what is sine squared? Well, sine squared x is 1 minus cosine squared x, right? So, okay, now that we have that, what should we make u equal to? How about this? If we make u equal to cosine, then du is minus sine x dx, right? And so this is the integral of 1 minus u squared times minus du. Does that make sense? I mean, you might not have thought of this, right? Like that's kind of a sneaky trick to take the sine cubed and to split it into a sine squared times a sine, and then to convert it to 1 minus cosine squared. You know, how do I know to do this? The honest answer is I saw somebody do it before me. I learned it from them. Now I'm teaching it to you. But yeah, then practice. Practice ingrained it. And I've probably taught about 20 classes where I've done this, but there's that. But anyway, I suppose teaching 20 calculus classes is not a practical method for studying for Calculus 1, is it? Unless you could get a job as like tutoring Calculus 1 while you're a Calculus 1 student, but that's trouble. It's hard to convince them to let you tutor the course you're taking, you know. There's certain ethical problems there. But I have had a Calculus 2 student before who could have tutored Calculus 2 while he was taking it. The fact of the matter is that boy did not mean to be in there. Anyway, so I just distributed the minus. Now we integrate. We got 1/3 u cubed minus u plus a constant, which of course is 1/3. U was cosine, right? So 1/3 cosine cubed x minus cosine of x plus a constant. There you go. And you can use essentially the same trick to integrate any odd power of sine, right? Let me not go through it, but like, so just the template, right? If I was integrating cosine cubed x dx, what would I do? I would say, well, that's really 1 minus sine squared x times cosine x dx, right? So I could do that for this one. If I had sine to the 5th power, I could do 1 minus cosine squared x squared times sine x dx. So like that algebra, and then for like the top one, I'd make a u equals sine substitution. For the other one, I'd make a u equals cosine substitution. The algebra would be much like what we just did. My point to you is this trick solves integral of any odd power of sine and cosine. And I think if you think about it for a second, you'll see that that's also true for cosh and sinh. See, because cosh and sinh have very similar properties, and you can trade cosh squared for sinh squared, because, you know, cosh squared minus sinh squared is equal to 1. So there's something similar that can be done for the hyperbolic functions. Anyway, we'll come back to these more. All right, so here's a problem that it's just a little bit annoying because it doesn't quite fit the pattern. Integral of dx over x squared plus b squared. We're assuming b is non-zero. What are we going to do in this here sad situation? Like, let me put it off to the side, what we know. Target, you know? Surely, like, intuition yells at me, this must be the integral of du over 1 plus u squared, right? Like, it's got to be this. This is the close thing to that. How do I get from where I am to where I want to be in yellow? Because I don't have a 1 plus variable squared, do I? How can I turn that b squared? That's a b, sorry. Here, okay, well, let's see here. Make it, I'll make it alpha. No, what's better? I'm going to stick with, I'll go to capital B. How about that? There we go. Is that better? How can I turn that capital B squared into a 1? How about, well, here's the trick. What if I factor it out? See, I have x squared over b squared, right? Plus 1. And so this is going to give me 1 over b squared, right? Integral of dx over, I'm going to rewrite it as 1 plus x over b quantity squared. Now at this point, I think you see what we want to make u equal to, right? What are we going to make u equal to? Right, yep, u equals x over b, very good. So that means du is 1 over b dx, or if you like, dx is b du. So this 1 over b squared integral of b du over 1 plus u squared, which gives us 1 over b, because the b's cancel, right? Inverse tangent of u plus a constant. And just finishing below here, so 1 over b inverse tangent of x over b plus a constant, and there you go. So in my book, the U-substitutions, which I would say are of moderate difficulty, require a moderate amount of algebra before you can make the U-substitution, you know. Show you another one. I'm going to erase this list here. Let's see here, so integral of x dx over x squared plus 6x plus 13. So with a problem like this, the first thing I'm going to do, well, I try momentarily, I at least give it a try to let u equal to the denominator, right? But what happens if you let u equal to the denominator? You get u equals to, let me just write it down here and I'll erase it. If I let u equal to x squared plus 6x plus 13, right? Then du is 2x plus 6 dx, yeah? And that's just not what I have upstairs, right? So it's not as simple as, always try that when you've got something like this. At least think about it. It fails, right? So that's not it. So since that didn't work, my next move is to complete the square in the denominator. So this is x plus